Hello everybody. Our lesson today is to talk about rates of change, particularly in terms of using the first derivative of a function. So we'll go through today what the definition for the rate of change is. We'll talk about how we actually solve rates, although a big component of today's lesson is we're going to feature the CAS calculator as much as possible. We'll talk about what graphs of functions indicate about the rate of change of that function. What types of units do we express a rate of change with? And as I just mentioned, using the CAS calculator today is fairly prominent. So if you've got your CAS calculator with you, it probably would be helpful. Today we're going to talk about the instantaneous rate of change, because this is the rate of change given to us by the first derivative. So the definition here is fairly textbook. The instantaneous rate of change of a function called f with respect to x when x equals a is given by f prime of a. In other words, the value of the first derivative when we substitute a. So in other words, the value of the derivative function at any point is actually the rate of change of the original function at that same point. Now just for a moment, I would like to talk about the average rate of change, just so we don't confuse this. So the average rate of change you've probably learnt before. We talk about this as a formula, which pretty much is the formula for the gradient between 2 points along a straight line. So it's the change in the function divided by the change in x. It gives us the average rate. So in this case, on this graph here, you can see between x equals 3, x equals 8, we're going to have the function of 8 minus a function of 3. The change in x is 8 minus 3. By the time we've computed that, we get a value of negative 0.5. And that is to say the value of y is going down half a unit on average for each increase in x. So as x increases, y goes down by half a unit. You'll notice that this definition doesn't actually use the derivative at all. So back to talking about the instantaneous rate of change. Let's have a look at this function. We've got just a parabola. Obviously it's increasing, and we can see from the slope of that curve that the rate at which it increases is changing all of the time. We reach a point at the top, and then the function begins to decrease slowly at first, and then more quickly as we go towards the right. So if we have the function for that curve and we find its derivative, we can calculate the instantaneous rate of change at each of those 3 points that I've labelled. So when x equals 3, the derivative is 2. And so right at this point in time, when x equals 3, a value of 2 is saying that y is changing twice as quickly as x. By the time we get to the top of the curve, when we've got x equals 5, our derivative is equal to 0. And of course this is how we define a stationary point, because for an instant, y is not actually changing as x changes. And at x equals 8, the value of the derivative is negative 3. And to put that in other words, we're saying that y is decreasing 3 times faster than x is increasing. And of course that was not the case immediately before that point, and even after that point that rate of decrease will be even higher. So we're only talking about an instantaneous rate of change. We use this terminology quite a lot in this course with respect to x, and in the problem we're about to look at, we'll see why it's actually a fairly important thing to keep including when we talk about the derivative with respect to x. So here I'm showing you a curve It's just one I've made up. I'm calling it the population of wombats in a certain area. So the curve maps out how that population changes with time. I'm using a function over here to describe that function, that equation, and it's a function of t, and in this case, as you can see on the x-axis, I'm measuring time in weeks. And that's going to be important when we talk about the units that we use to express a rate of change. For this particular graph or function, I'd like us to look at 3 questions. We're going to work out at what rate the population is changing after 20 weeks. We're going to solve exactly when the rate of change was equal to 1. And 1 what? That's what I'll talk about in a minute. And the third question we'll look at is when was this rate of change a maximum? Exactly when does this occur, and what was that maximum rate of change? So the first question, at what rate is the population changing after 20 weeks? As I said, I'm going to use the CAS calculator to answer these questions. The function is fairly complex. So using the calculator, having defined the function, I've found the derivative of the function at a point where x equals 20. In other words, I've found f prime of 20, and we get a value of 1.5729. Now, because our function described the population of wombats and t was in weeks, the units for this rate of change is 1.57 wombats per week. So when we look down at the graph, we can see 20 weeks, at the end of 20 weeks on the horizontal axis. We've got the point on the curve here. You can see the population was slightly above 20 wombats, but at that precise point in time, the population was increasing by 1.57 wombats per week. That's not to say that in the next week the population of wombats is going to go up by exactly 1.57, because immediately after this point in time that rate has already increased. So it's what we mean by an instantaneous rate of change. And you can see here just on the calculator, if you'd like to pause it and work through that yourself, how I've defined the function. I can find the derivative if I want to, but here I've actually calculated the value of f prime of 20. The second question, exactly when is the rate of change equal to 1? So along this curve there must be some point where the slope of the curve is equal to 1, the gradient is equal to 1. In other words, that rate of change of wombats is exactly equal to 1 wombat per week. So on the calculator, I've used my calculator to solve this equation. So the derivative of f of x is equal to 1. That's when my rate of change is equal to 1. I'd like to solve x, in other words, the number of weeks. In the context of this problem, we could say we're solving f prime of t equals 1 for t. I'm using x on the calculator, not t. The calculator gives us 2 solutions to this equation, roughly 12.4 and 47.6. So down here on the graph we can see there were 2 points in time during this period when the rate of change of wombats was 1 wombat per week. So after 12.4 weeks, immediately after that the rate increased, but at some point it started decreasing again. Population kept increasing, but the rate at which it was increasing was going down. To another point at 47.6 weeks, when again the rate of change was 1 wombat per week. And our third question, exactly when does the maximum rate of change occur, and what is this value going to be? So there is a point, and there's a certain symmetry about the function that I've chosen today, but there is a point somewhere around here where you can see the graph is getting steeper, that then it must stop getting steeper and flattens off again. Okay, we could also say that the curvature changes here on this side of the curve. We've got a concave up sort of curve. By the time we're over here, we've got a concave down sort of curve. For those students who are aware of the second derivative would help you find this position, this point in time, but we're going to use the first derivative only, but also the help of the calculator and its graphing ability. This is what the graph of the derivative looks like, and I've purposely put it directly below the graph of the function. So the top graph shows us how the population is changing, while the graph underneath tells us how the rate of change is changing. Notice the rate of change is always positive, so the population is always increasing, but at some point it's increasing faster than any other point. And so we've got this maximum value on that curve. Here I've plotted that same derivative on the calculator, and I've analysed the graph to find the maximum value or the maximum point on that curve. The coordinates we get are 30 and 2. And it's important, the examiners would like to know that we can interpret that information. So that is to say that the maximum rate of change is 2 wombats per week. And that occurs precisely after 30 weeks. So just to conclude, we've defined the rate of change, at least the instantaneous rate of change, and it uses the first derivative, and we're aware that that's different to describing the average rate of change, even though the two are related. We've solved rates using the first derivative. We've also taken advantage of the calculator to do that. We've been able to look at the graph of a function and look at the steepness of the curve, whether it's increasing, whether it's decreasing, to talk about how the value of that rate of change is behaving. We had a talk about what units we use to express the rate, and this comes from what units are we using to express the function. In our case it was wombats, with respect to the variable that function is being measured against, which in this case was time in weeks. So our rate was expressed as wombats per week. And we've done a bit of work with the calculator in particular, where we've defined functions and used the calculator to find derivatives and solve equations. Please write down any questions you would like me to go over or things you'd like me to re-explain. And of course, complete the Google form, find out how good your understanding of this concept is at the moment, and log your attendance. Thanks very much.